Hello, everyone. Today, I'd like to walk through how to think about scalability in system design. Scalability is not just about adding more machines. It's really about understanding where bottlenecks come from, choosing the right scaling strategies, and balancing trade-offs between performance, consistency, and cost. When thinking about scalability, I usually break it down into four dimensions. First, horizontal versus vertical scaling. Second, stateless versus stateful components. Third, data layer scaling strategies. And fourth, auto scaling and traffic spike handling. Let's go through them one by one. Let's start with horizontal scaling. Horizontal scaling means adding more machines to distribute load. In most modern distributed systems, this is the preferred approach. We typically scale out by adding more stateless service instances behind a load balancer. This improves availability, removes single-node bottlenecks, and fits naturally with cloud-native architectures. Of course, it also introduces new challenges. We need effective load balancing, stateless service design, and proper strategies for data distribution and rebalancing. Now, let's look at vertical scaling. Vertical scaling means increasing the CPU or memory of a single machine. It's simple and doesn't require distributed coordination. However, it has clear limitations. It's bounded by hardware capacity, can introduce a single point of failure, and becomes increasingly expensive at higher tiers. So, in practice, vertical scaling is often a short-term solution, while horizontal scaling becomes the long-term strategy. Next, stateless versus stateful components. Stateless services are ideal for scaling. They don't store session data locally, so instances can be added or removed dynamically without impacting correctness. This makes them a natural fit for auto-scaling. Typical examples include API layers, gateways, and ingestion services. Stateful components are more complex. They require sharding to distribute write load, replication to scale read traffic, and careful handling of rebalancing and data migration. Examples include databases, caches, and message queues. So the key idea here is stateless components scale easily, while stateful components require careful data partitioning and coordination. Now, let's look at the data layer. For traditional SQL databases, we typically scale reads using replicas. However, writes are often constrained by a single primary node, which can become a bottleneck. Sharding is possible, but it introduces significant complexity. In contrast, distributed or NoSQL databases are designed for horizontal scaling from the beginning. They use partitioning or hash-based distribution to scale out. But they also introduce new challenges such as hot partitions and rebalancing overhead. So in practice, it's important to continuously monitor data distribution and ensure that load stays balanced. Now, let's talk about auto-scaling. Scaling policies are usually based on metrics like CPU usage, memory usage, request rate, or latency. When thresholds are exceeded, new instances are automatically provisioned, and during low traffic, we scale in to reduce cost. However, auto-scaling is not instantaneous. During sudden traffic spikes, we may see cold start delays and temporary overload. To handle this, we typically introduce buffering and protection mechanisms. Message queues to absorb bursts, rate limiting to protect the system, circuit breakers to prevent cascading failures, and gradual traffic shifting. The key idea is to stabilize the system first, while scaling mechanisms catch up. To summarize, when thinking about scaling, it's important to distinguish between stateless and stateful components. Stateless services scale horizontally behind load balancers, while stateful components rely on sharding and replication. At the same time, we need to monitor for uneven load distribution and proactively handle traffic spikes. Scaling is not just about adding machines. It's about maintaining balance, consistency, and efficiency as the system grows. To conclude, scaling is fundamentally about removing bottlenecks while preserving correctness. The real challenge is not just scaling out, but scaling in a way that avoids hot partitions, reduces coordination overhead, and maintains system stability. Thank you.